Hello everyone, we are about to make our third acid-base theory video, and here we are going to extend our discussion to look at factors that that alter the acidity and basicity of species. So I will bring up these notes again. These notes are shared with my students, and I will annotate them here for their convenience. Okay, so we are going to start. So previously we mentioned that some materials can be amphoteric, and we can definitely extend that topic here by looking at salts and the acid-base nature of salts. So salts, on the one hand, we have to be careful here. Salts, by most definitions, are neither acidic nor basic. So for example, here we can see, let me get this pointer so we can see where I'm looking at. Yeah, we can see here that the term salt refers to any ionic compound that does not contain a proton as the cation or hydroxide as the anion. So by not containing the proton, we would say it's not acidic. By not containing the hydroxide, we'd say it's not basic. Therefore, it's something else. However, salts can actually hydrolyze and do other things. Salts can actually be acidic or basic or neutral. So it's kind of, I just want you to be careful about thinking of salt as the third type of ionic compound after an acid or a base. It's not quite that straightforward. So one of the things we're going to do is to look at what it is about certain salts that give it acid-base character. So probably we'll start here. Okay, and this will make sense. So predicting the acid-base character of salts. So it says anions of strong acids and cations of strong bases have no acid-base character. This makes sense because they are shifted far right. So this makes sense since whatever the equilibrium constant is, it's much greater than 1. Now, why would that mean anything? Well, it says the anions, so the anions, here the anions would be conjugate acids. Oh, sorry, this would be the conjugate base, right? So the anion of a strong acid is the conjugate base, Cb. And the cations of strong bases, these would be conjugate acids. And we said in a previous video that if K is greater than 1, the argument, which is the thing on the left of the arrow, the argument of the expression is stronger than the conjugate system, or the Brensted-Lowry system would be stronger than the conjugate system. So it goes to show, if we're already saying that the acid is strong, we're saying the Brensted-Lowry system is stronger than the conjugate system. And therefore, we assume that the conjugate system doesn't do anything. It's stable. It's not really imposing its will on the Brensted-Lowry system. So have a think about that, and hopefully you'll see it makes sense. Cations that are conjugate acids of weak bases are acidic. We'll look at this in a bit more detail when we look at aqueous equilibria, which is not in this video sequence. But essentially, it will undergo hydrolysis. So I'll mention it briefly here, but we will look at this in a bit more detail later on. So for example, cations that are conjugate acids of weak bases are acidic. So this would be, so a weak base, this would be, I guess, this cation would be the base that picked up the H. So that would be BH plus water to give H3O plus the base again. Let's say base minus to keep it neutral. So it would hydrolyze and it would form an acidic solution because of the hydronium. And then the anion, let's say this is A minus. The anions that are conjugate bases. Okay, so the anion, this would form A minus plus water. This would form HA plus OH minus. And it's basic because you form OH minus. Okay, but much more about that in subsequent sequences of videos when we look at aqueous equilibrium. Okay, let's scroll. Okay, both ions of a salt could have acid-base properties. So here's a nice example. So ammonium phosphate. So when you have these polyatomic ions, you can look at each ion sequentially. And we can see here, if I use my pointer, we can see here that if we look at the ammonium ion separately, ammonium itself has its own equilibrium state. So ammonium plus water gives ammonia and hydronium. And because this is an acid in its own right, we would expect the extra synthesis of hydronium in solution would, so what am I trying to say here? Oh no, sorry, ignore that. Yeah, ignore that. Okay, so look, I was confusing myself with my own notes. Look at this at the end. So this will be our little conclusion. So we're not quite ready to conclude yet. This will be our conclusion. Okay. So ammonium plus water gives ammonia and hydronium. And then phosphate, well, it can't possibly be an acid, right? Because there's no H, but it can be a base. So phosphate can mix with water to give HPO4 2 minus. So we've added an H plus. So we've lost a negative charge here, and we get hydroxide. Now, looking at the K values, we're told here a priori that the phosphate ion is a stronger base than the ammonium ion is an acid. So the Kb value for the phosphate is a greater number than the Ka value for the ammonium. Therefore, although both ions produce hydronium and hydroxide respectively, because Kb is larger than Ka, we expect a greater concentration of hydroxide. So the concentration of hydroxide is greater than the concentration of hydronium. So overall, we have a basic solution for this salt. So here, both anion and cation contribute to the pH, but the anion has the greater contribution. Okay, so moving on with this video. So this was a nice insert I found, and rather than just write everything, I'd rather just post it and draw my students' attention to it. So just to remind us about the Lewis acid and base definitions, recall from a previous video, a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. Here we're going to look at different oxides, both metal oxides and non-metal oxides. So first of all, if we look at the oxides of most nonmetals, we can see that these are actually classified as acid anhydrides. So that essentially means they're acidic when mixed with water. So if you take dinitrogen pentoxide as a first example, which is a nonmetal oxide, you add it to water, you can see that you form nitric acid, which is a strong acid, which will completely dissociate to give protons and nitrate. Obviously, the protons won't be like that in equilibrium. The protons won't be that really in the beaker. They'll be hydronium ions. So this will really be hydronium. But in short, the principal species will be on the right. So this will actually be hydronium, right? So these would be the predominant species. Sulfur trioxide, you can see over here, is a nonmetal oxide. Let me get my pointer back. Sulfur trioxide is a nonmetal oxide. And when it adds to water, it will form, so you could bubble this through water, for example, you would form sulfuric acid, which is a strong acid, or at least the first proton is. And that would form a strong acid and a weak acid that could go on for further equilibrium, diprotic acid here. So we can therefore retroactively classify these nonmetal oxides as acid anhydrides. Anhydride just means they lack water, but when you give them water, they can produce acids. Let's clear, actually no, let's just scroll. Let's look at the oxides of metals. So let's move away from nonmetals. Let's move away from nonmetals, let's go to metals. So here we've got oxides of group 1 and group 2 metals. So these are the S block metals, or group 1 are the alkali metals, group 2 are the alkaline earth metals. These are base anhydrides. So they're anhydrides means they don't have water, but when you put them in water, they produce a base. So for example, calcium oxide, which is a group 2 metal oxide, when you add water to it, you form calcium hydroxide, which calcium hydroxide has a low solubility, but it would be a source of hydroxide if it dissolved. Okay. Let's see if I can scroll. Yes. So we know that nonmetal oxides are acidic anhydrides. And we've just seen, or we're told that the antithesis, S block metal oxides, are basic anhydrides. What about the metals in the middle? So a metal in the middle, an example at least, is aluminum. These can be like a mixture of the two under different circumstances. So something in the middle, like aluminum, can be amphoteric. That's vocab we've seen previously. It means it can be both an acid or a base. So aluminum oxide, Al2O3 shown here, can act as a base. So here we have it acting as a base in the presence of an acid. It potentially could produce a salt and water. So here's the water. So this you could think of as a neutralization reaction. An acid and a base gives a salt and water. Here we just don't have a counterion for the aluminum. And here we've got the same chemical, aluminum oxide, acting as an acid. So we can take this as an acid, we can react it with a base. You get a salt and water. Here the salt doesn't have its counterion, the cation, but that would just be another species in solution. So again, we have the nonmetal oxides on the acidic end, we have the metal oxides on the basic end, and there's materials in the middle of the periodic table that are more amphoteric in nature. So here is a nice summary diagram. And just in case the visibility wasn't that great, which I guess it's not, I've rewritten it down here. So we can see here we've got group 1, lithium, sodium, etc. Group 2, this would be beryllium through barium, etc. And we know these are the base anhydrides. We saw an example just a few moments ago of dinitrogen pentoxide. So these nonmetals would be acid anhydrides. We've just seen aluminum oxide in the middle, and you can have essentially this continuum, increasing basicity down a group. So there's, somewhat of a periodic trend here, increasing basicity down the group, and right to left across a period. So essentially, I guess if we were to look at a periodic trend here, if we tried to summarize this trend, succinctly, I guess we could say, if we went like this, we would have a diagonal. We'd have the acidic end, and we'd have the basic end, right? So we'd have that continuum. And you can argue that it's a trivial argument based on, you can just think of the ionization energy of these, or the relative strength of these elements, and you can trivially argue why they follow that trend. Okay. So let's scroll away to the next page. This is just a half page I thought was nice, and I included it for the benefit of my students. So we've just seen some oxoacids that were the oxoacids were the nonmetal acid anhydrides. And hydroxides are Arrhenius acids and bases. So we've just seen that, again, according to the Arrhenius definition, you produce protons and hydroxide in solution. The protons generate hydronium ions. And that's what we could find from these oxoacids, or these acid anhydrides. The problem is, though, they don't actually contain protons themselves. So strictly the Arrhenius definition is you have protons, and that's what generates hydronium ions, but we don't actually possess the protons to begin with. So there's a subtle difference between the definitions here. So it's a unique type of acid and base property. So, one, not to tell you what an exam question might be, but given all the types of acids and bases that we're starting to see in these videos so far, you could be asked to briefly compare and contrast the definitions of acids and bases, whether it be Arrhenius, Brensted-Lowry, Lewis, or these oxoacids here, etc. Or you could be given a chemical and asked to classify which, some kind of Venn diagram. What type of properties do they have in common? Which are the unique properties that they have? Let's consider this, which is from the previous page, it's a group 2 metal oxide, so it's a basic anhydride. So calcium oxide here, instead of adding it to water, like we did on the previous page, instead of adding it to water, we can see that we just add it to another molecule. So this is aprotic. It's not even in the aqueous phase, right? So we've got basically a metal oxide and a non-metal oxide. So let me annotate over this real quick. So by the previous page's definition, we said that this was a base and this is an acid, right? The non-metal oxide was the acid, the metal oxide was the base. And we can see here that we form a salt. We don't form water because it's aprotic, or it's not aqueous. So we don't form water, so it's a form of neutralization, I guess. But here we can see that the calcium oxide donates an electron pair to the CO2 to form a coordinate covalent bond. And we've seen this on a previous, when we looked at Lewis acids and bases, we saw that, let me do it down here. We saw that CO2 can form this type of structure. So the carbon can be receptive to a lone pair from the calcium oxide. So if I can scroll, I can never scroll once I write, which is definitely unfortunate. Let me change color though. Let's do that. So you can see that the calcium oxide, you can get some kind of lone pair addition here. And then you can basically see how that extra interaction with oxygen and carbon is coming about. And this whole structure here would be the calcium carbonate. Okay, so we've seen that type of thing before. This would be the coordination bond, or the coordinate bond, sorry, and this would be an adduct. Notice though that this is not redox, and I think back when we looked at Lewis acids and bases in, I think it was video 2, actually no, video 1. In this sequence, we saw that although we are, electron donating and electron accepting, which kind of sounds like redox. Remember, Lewis acid-base theory is not redox because there's no change in oxidation state. So we're reminded here that this is not redox chemistry, although we are exchanging electrons. So this is although electrons are moving, and here moving just means they're being donated and accepted, so they're just moving. So this would definitely fall under acid-base theory because of the analogy that we've just seen here. Okay. So let's go back to our scrolling. Okay, so here, let's look. So some of this is a little bit of a duplication, but it's a slight repetition, but then hopefully a slight expansion on things that we might have said in previous videos. So the acidic nature of metal cations, we said that metal cations are always going to be classified as Lewis acids because they can accept electron pairs to different extents. But here we're going to see a bit more about how it actually operates, and it's a bit more involved than you might initially think. So we typically want small ions with a high charge, so a high charge density. So these would all have a high charge density. So high charge density. That's going to allow them to produce a polarizing environment, and that's going to be important here. So, for example, we take aluminum, an aqueous solution of aluminum. Well, that's going to immediately be in the bulk water, and it's going to form a hexa-aqua aluminum complex. So it basically forms, and I'll have to scroll so you can actually see it. It's going to form something like this, which you'll recall from a previous semester of general chemistry as an octahedral structure, or an AB6 structure, where we have aluminum in the middle, and we've got 6 water molecules here. Notice the orientation. The more electronegative oxygen is approaching the electron deficient center here, the aluminum. So we've got the 6 water molecules here. Now, if we think about the interaction here between aluminum and water, this can be an equilibrium where one of the water molecules can actually, or the attraction of the aluminum for electron density in an OH bond can actually weaken the OH bond sufficiently in water to liberate a hydronium, or a proton here, which eventually is going to produce a hydronium ion. So one of these bound water ligands is going to become a hydroxide. The hydroxide has a single negative charge, so that's going to overall reduce the net +3 charge to a net +2 charge. Remember, it's not redox though, because the charge on aluminum, the oxidation state rather, on aluminum is still +3. So although it looks like we've gone from +3 to +2, we haven't. We've just mopped up one of the negative charges by hydroxide. So we haven't done any redox here. This is just acid-base chemistry, Lewis acid-base chemistry. Okay, so this is adding a bit more detail to what you might think about just accepting a pair of electrons. You can see that we do actually produce protons, which would generate hydronium ions, which would lower the pH, etc. Okay, and I put an asterisk on this bullet point here. This is important, and this will definitely become continue to be important moving forward as you leave general chemistry and head into organic chemistry. The strength of an acid or a base is inversely proportional to the strength of its conjugate base or conjugate acid. This makes sense from an equilibrium point of view, so let's just comment on it briefly. So it makes sense, right? If you have a general acid and water in equilibrium to give hydronium and the conjugate base, well, if this is stable, it will be essentially excluded from reverse reaction, right? If it's quite happy to stick around, it's not going to interact with the hydronium again or anything else to generate HA. So if we think that equilibrium, so if we assume that Ka is a lot greater than 1, then equilibrium is shifted far to the right, favoring product. If A minus were not stable, it would shift left again and it would lower K. So not only does this make sense, but it has to be this way to be internally consistent. So I'd encourage my students to think about the statement, think about what being a strong Brensted-Lowry acid means. It means shift far right. That means not shifted back to the left again. So that means you don't consume the products, because if you consume the products, you would shift left. And that would mean that the products can't be stable. So it's all internally consistent. If we were to just do a quick summary now, we've done this several times, but let's keep adding. So I'll do it for acidity, but you could do it for basicity as well. Acidity is proportional to hydronium, is proportional to Ka, is proportional to 1 over pKa, is proportional to 1 over pH, is proportional to, let's get it right if we're going to do it, is proportional to conjugate base stability. So I guess this is the new feature here. It's conjugate base stability. So you can think of these proportionalities. Okay. All right, so moving on. We've got about 5 more pages left. Not too much, but 5 pages. Anyway, so we've seen some of this before. Remember we said that the product of Ka and Kb is equal to Kw. And I won't belabor this. I think I actually went over this in video 1. But just quickly, if you take a generic equation, Ha plus water to give hydronium and conjugate base, you can write the law of mass action expression or the acid dissociation expression, Ka. Then if you take the conjugate base and that you hydrolyze it to generate a Kb expression, whenever you add equations, you take the product of K values. So I won't belabor it, but I'll just briefly summarize. So you add equations. That means you take the product. You take the product of K's. And you can see here that when you take the product of K's, certain things cancel. You've got Ha as a numerator and a denominator. You've got A minus as a numerator denominator. You're left with hydronium and hydroxide, and that by definition is Kw, which is 1 by 10 to the negative 14 at 25 degrees Celsius. Okay. So we've seen that in a previous video. Why are some acids stronger than others? Well, definitely some acids have a more stable conjugate base than others, and all the other reasons we've elicited so far. But there are some reasons we haven't elicited, or some features. So I would definitely view this like, to give you an analogy, why are some carnivores better adapted to catch prey than others? They might have longer teeth, they might have pointier teeth. So you can look at the feature of the carnivore and see why it's better at doing what its family says it should do. Likewise, within the acid family, why are some members better at it than others? So we've already seen that strong acids ionize completely. and therefore generate a higher concentration of protons, which generates a higher concentration of hydronium. Well, if you release more protons, you must have more ionizable protons. That means you must have more labile or more active hydrogen atoms. And why might that happen? You might have a weaker bond. So this could be, you know, a weaker bond. You'd expect a weaker bond. You know, bond strength and acid strength are inversely proportional. So if you have the bond between some chemical X and H, and that's the bond you want to break, so this bond here is proportional to 1 over acidity, because the stronger it is, the harder it is to break, and the less of it will break. Conversely, if you want a weak bond, you want a highly polar bond, right? So if you want a stronger acid, you want a weaker, weaker with an A, weaker XH bond. So you want a polar bond. So for example, you want something that will generate a polar bond, so X could equal oxygen, and we've seen lots of acids with oxygens in, for example. So you could have oxygen. So for example, you know, if it were oxygen, just looking at electronegativity values, we know that oxygen on the Pauling scale is 3.5, oxygen is 2.1. So we know that this difference of 1.4 being greater than 0.5 means it's polar. We could annotate that the way a chemist would. And we would say, obviously, that we have a delta negative oxygen, a delta positive hydrogen. And so although it's not ionic, it's definitely weakened. The electron density between these two nuclei are being pulled unfairly towards oxygen. And this is starting to look a little bit like H+. Okay. So let's look at these binary acids for halo acids. So starting at the top of the halogen side, or the halides, we have HF, which we know from previous videos and life experiences is the only weak member. So this is a weak acid, but all the other members are strong acids. And we can see that as the bond gets stronger, the acidity gets less. So as the bond strength gets stronger, here bond energy is the bond strength measured in kilojoule per mole, we can see that we get less and less acidic, and eventually we cross over from strong to weak. So our K value is less than 1 for HF, but it's greater than 1 for the others. And we can see here, once it's measured against pKa, we know that pKa is proportional to 1 over acidity, or acidity is 1 over pKa. So we can see here that the smaller this is, it's going to give us a larger acidity. And the larger this is, it's going to give us a lower acidity. Also, you can think of Coulomb's law here. So we know that if we look at H, so let's say this is not the scale, but let's say these are the H atoms, and then we've got F, Cl, Br, I. So X, where X is F here, Cl, Br, and I, then we've essentially got the bond length. So let's call this bond length R. R increases as you go down this group here. Okay, so just from a Coulomb perspective, well, we know that the force is proportional to 1 over R squared. So here, F is proportional to bond strength. Force between these objects. Then as the bond length R increases because the atom is just getting larger, then R squared is going to get larger, 1 over R squared gets smaller, so F gets smaller. Or we could say F gets larger that way. And so the greater F, we know that acidity is proportional to 1 over F, which is proportional to R. So there's different proportionalities that we can look at. So you can pause this video, have a think about all of that good stuff. Meanwhile, in real time, on we go. Some other structural factors. Yeah, I think we've just started to look at the size of the anion. So we've just started to look at that. The size of the anion will lead to bond length. That is proportional to R. So we've just seen that recently. Electronegativity, we just had a look at that. That would weaken the bond. So this would increase the polarity of whatever the element is with H and weaken the bond. I think we've just looked at that. What else? Small anions have, yeah, and you know, if you cast your mind back to the last time we looked at some quantum mechanics and orbital overlap in the previous semester of general chemistry. You know, if you consider sigma orbitals where you've got, you know, the orbitals overlap face to face rather than pi overlap, which is parallel. We know that not only is the orientation important for overlap, but the size can impact the energy. So if we look at the 1s orbital of hydrogen and the 2p orbital of HF, so let me scribble some kind of diagram here. So let's say this is the 1s orbital of hydrogen, and then let's say that's the 2p orbital of fluorine, and here's the little overlap here. This is the sigma bond. This is obviously not to scale, but just to give you a visual of what we're talking about. Now, if you compare this with the S of hydrogen and then the P of the 5p of something like iodine, then there's going to be less overlap. It's really not intuitive the way I'm drawing it. But the overlap here will be less. So I'm going to call this sigma prime, where sigma is greater than sigma. Oops. I cannot write and draw at the same time. There we go. Where sigma is greater than sigma prime. And that's to do with the energy level, right? So the energy level 1 and 2 are closer together, but the energy level 1 and 5 are further apart. So they have less orbital overlap, and therefore easier to break. So the sigma prime bond is weaker. So this is weaker. And obviously sigma is stronger because they have more similar energy levels. Okay. Okay, so scrolling on. So I think we've already summarized this, where we saw that the going down the halide, the halogen group, as the anion gets larger, the bond gets longer, the overlap gets weaker, the bond gets weaker, and therefore it's easier to ionize and generate hydronium, so the acidity increases, as noted here by the pKa. Remember, pKa is inversely proportional to Ka, so as the pKa gets smaller, the Ka gets larger, shifted farther right, etc. All those interchangeable ideas that are saying the same thing in different ways. I think we've already talked about the electronegativity difference. Something like oxygen, which is highly electronegative, will form a polarized bond with hydrogen and will allow it to generate a more highly polarized bond, and therefore a weaker bond. And we'll see that with some examples here. So let's take carboxylic acids. So acetic acid here, the main chemical in vinegar. Acetic acid is a carboxylic acid. And let's see, do we have the resonance structure? No, we don't. So let's annotate this with its resonance structure. So if I just call this, if I just call all of this stuff R, so I'm going to call this R COOH. Now this H, this is a weak bond, so this could become a minus and a plus, right? So if I have this, not the principal species because it's weak, so the intact chemical will be the predominant species. But if I have something like this, this can resonate, form a resonance structure with, I should know better than to talk and write. Thusly, let's change the color here a bit. So I could have, so this would be a resonance here. Now this is resonance. We know from, I don't know, grade school somewhere, that resonance leads to stabilization. So this is a carboxylic acid. So resonance stabilized. Now, what's resonance stabilized? Resonance stabilized conjugate base. So remember, one of the things that's proportional to acidity is the stability of the conjugate base. Now, this is stabilized, but it's not. It's still a weak acid. So carboxylic acids are generally weak, despite having resonance stabilized conjugate bases. But they're a bit more they're a bit more acidic than they would be. So for example, you know, because of this resonance stabilized conjugate base, they're generally weak but stronger acids than chemicals with just an OH group. So typically alcohols. So alcohols are substances with an OH, just like a carboxylic acid has an OH. The difference is a carboxylic acid has an adjacent carbonyl, and the presence of an adjacent carbonyl allows resonance stabilization, which further stabilizes the conjugate base compared to just RO negative. And that increases the stability of the conjugate base and therefore raises the acidity compared to a general alcohol. We can fine-tune the strength of the carboxylic acid as shown here. So we have a general, these are all carboxylic acids, as you can see by the OH and the adjacent carbonyl. So from this end of the structure, we can tell they're all carboxylic acids. Here we have just carbon with 3 H's. Here we start to annotate carbon with a Cl, which is more electronegative, carbon with 2 Cls, and carbon with 3 Cls. So we've got acetic acid, chloroacetic acid, dichloro, because we have 2 chlorines, and then trichloroacetic acid, because we have 3 chlorines. Look at the effect on acidity. So acidity is increasing this way, because acidity is proportional to Ka. So although we're still weak, because we're carboxylic acids, we're able to fine-tune how weak we are, and we're getting a bit stronger. Why? Because we're essentially stabilizing the conjugate base. So what's increasing down here is the CB stability. As the conjugate base stability increases, the acidity increases. Yeah, so for example, when we have the conjugate base here, so let's in general say that this stuff, let's use a different color. Let's say that all this stuff in purple, I'm just going to say it is whatever it might be, it changes for each one. Let's say all this stuff is R. Then we are able to pull electron density away. So essentially, we are able to stabilize. So not only are we able to, essentially, I'm stabilizing this negative charge, right? So this negative charge can be stabilized not only here on this oxygen, but it can also be stabilized. It can be pulled in this direction as well by these more electronegative chlorines. It would be even better if we use fluorine, but it can be pulled in this direction, essentially away from being isolated and, again, away from the danger of we just want to prevent it mopping up the H+. We want to stop that, right? So if I can pull it away and keep it locked away inside the structure, I'll prevent it mopping up the H+, and that will increase the acidity. So let's see. And yeah, so the types of acids we've seen before, oxoacids, we can definitely increase the strength by, again, continuing to stabilize the conjugate base. So for example, I think a specific one we saw was this bottom one here, right? So we've seen that HNO2 is weak, but if we increase the stability of its conjugate base by adding more oxygen, more electron withdrawing species, we can have a strong species. Remember, a weak species, that's the predominant species. A strong species, it would actually be H3O plus NO3 minus. That would be the predominant species. More examples here. Again, you've got hypochloric acid. Where you've got HClO as the predominant species. This would be perchloric acid. It's strong because of the more electron withdrawing oxygens stabilize the conjugate base. And so once that proton has been donated, it's nothing to receive it again. And the predominant species here would be H3O plus, and then perchlorate, ClO4 minus. Binary acids. Here we've got ammonia. Ammonia is not an acid, but it's a binary compound. It contains hydrogen with something else. Water contains hydrogen with something else. HF contains hydrogen with something else. So it's binary. It's a collection of two different elemental types. We know that electronegativity increases from the bottom left of the periodic table towards the top right, with reducing metallic character. So, if we look here, I guess a little diagram would have been helpful. So let's put one in. So we've got N, O, and F. So this is in period 2, right? Period 2. We've got NO and F. In terms of electronegativity, let's see if I can remember my electronegativity values. O is 3.5 on the Pauling scale. We've got 4. We've got 3. So these are the electronegativity values. And so they're roughly the same size. Let's assume that they are the same size. And so you've got the NH bond, the OH bond, the OF bond, sorry, not OF, HF. See, I was doing that talk and write at the same time. NHOH. That should be FH. And you can see here that it's weaker. So this bond is stronger. And so you can donate. And then these bonds are weaker, so there's more likely that they will be broken. And again, just looking at the relative effect of polarity and the relationship between polarity and bond strength. So polarity is proportional to 1 over bond strength. And we know that bond strength is proportional to 1 over acidity. Okay. And then in the final page of this video, I think this just summarizes it. So let's see, what is this? Okay, so it looks like we have plotted pKa values. Remember pKa values and their proportionality to a, let's see, pKa, remember, is proportional, well, Ka is proportional to acidity, so 1 over acidity. All right. So here you've got the pKa values. These are these numbers here. So as we just saw, we've got basically increasing acid strength, or conversely increasing base strength over here, acid strength over here. So, and then down here, why would it increase acid strength here? Remember, we're just getting longer bonds. So there's definitely different ways you can argue acidity. We're looking at polarity here. So essentially, we're looking at polarity, bond polarity within a group, within a period. Within a period. And we're looking at bond length within a group. And you know, there's many ways you can look at these things, but ultimately I would encourage you to think of how long is the bond, how weak is the bond, how mismatched are the energies within the bond, how stable is the conjugate base. Look at all of these together when you try and interpret bond strength. Is there any resonance, stabilization, etc.? And that will conclude this video.